the webinar.
I'm showing 1 minute.
Okay. In about 30 seconds I will start the broadcast.
Okay.
After the woman talking, you can go ahead. People will also hear you. So Mike, I will be launching the broadcast. Success.
Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody, and thank you for joining us for today's webinar, 1-hour webinar, using Optimus with JMAG Designer to get the best value from your electromechanical design simulations. This is a part of our series that we do every month on various subjects. My name is Mike Nieberg, and I'll be your host for today's session. Everybody has their mics muted at this point. We have a large audience, but I would like to encourage everybody to send over any questions that you might have at any point during the webinar. You can do that in the control box that you'll see to the right of your screen. So please type in any questions. At the end, we will have a few minutes to go through as many of those questions as we can. I'll begin by doing a very short introduction of Optimus and Noesis. I'll be followed by David Farnia, who is with JMAG and PowerSys, and he'll provide an introduction of JMAG. And the bulk of the presentation will be done by Taylor Newell, who will be going through some application cases, optimization of a 2D actuator and a 3D surface permanent magnet machine. And then, of course, as I mentioned before, we'll have the Q&A session. Optimus is a process integration and design optimization software, sometimes referred to as PIDO. It automates the simulation-based design process, and the benefit that it provides the user is reducing the overall time by an average of 30%, while at the same time allowing you to get higher performance from your designs, average of 10%. Optimus is the most extensively deployed software of this type, this PIDO variety, and we're heavily used in all industries, showing some examples there in the automotive, aerospace, and then all other industries. Of course, anywhere where you're doing simulation-based design, Optimus can potentially be a benefit. We are a leading software and services provider. We not only provide Optimus as a tool, but we also license our optimization technology to a number of third parties that use it for what I would call push-button optimization. The reason that's important is we've had to put a lot of emphasis into developing very robust techniques with minimal involvement by the user. So it's an engineering tool where you have limited number of choices that work very, very well. We're completely independent. We're not owned by any other company. Optimus is our only product, and this allows us to be very, let us say, agnostic in our ability to work with multiple vendors. We've got offices all across the world. Here in the U.S., we're in Carmel, Indiana. In Europe, we've got offices in Belgium, Germany, China, Japan, and all across the world, as you would expect. Okay, so my introduction here on Optimus itself, what I'm hopefully going to show you is give you some insights into how you can reduce your overall simulation time, reduce the amount of time that the engineer is putting into non-value type work, but also improve the performance of your designs. To enable you to do that, Optimus actually possesses a number of different capabilities which can be used either independently or in a combination. And in addition to that, there's customization that's possible if necessary. So let's start with the first of these, which is process integration. This capability allows you to link any number of programs together and allow it to run as one continuous and automated workflow. In this example, you'll see going from the left to the right, you have a CAD package, goes into a specialized, in this case, CFD package called NUMECA, as well as structural analysis being done with ANSYS and post-processing by ANSYS. All these programs are now linked together without the user having to work and independently set off each one of those programs. All the file handling is handled, and this runs automatically. So this can run at night, over weekends. It is also very controllable. You can put in logic to prevent it from doing further steps if earlier steps are not acceptable. And of course, you now have a repeatable process that can address, for example, Excel files without people having to search around to see if they have the latest one, and so on. So this process integration capability is by itself a major advantage of using Optimus. Now, in terms of the technical engineering capabilities, there are a number. The first I'll talk about is design of experiments. In my experience in meeting with hundreds of companies doing simulation-based design, I've found that DOE is something that is often, in my opinion, underutilized, and it is because of the inability to run these efficiently is one of the reasons. So just to give you a quick insight or overview of DOE in case you're not familiar with it, if you see this chart on the right, it shows a design space, and with a DOE, you're going to run a series of samples. In other words, different parametric combinations to look at the results. You can use that data in a number of ways, and Optimus makes this very, very easy to do. First of all, Optimus will define which designs it should run. You merely specify the number of designs. So if you said, for example, I have the time to run 40 different cases, Optimus selects which 40 parametric combinations to run. After that's done, it will provide some useful information. In this sample that we're looking at right here, we're looking at a 1D diesel injector valve where the design variables are the diameter of this inlet area, which is blue, the angle of the poppet valve, which is yellow, the diameter of the poppet injector, which is red, and how long this thing is open. On the left, we see a chart, color-coded chart, and what you're looking at here is a correlation between each of those design variables as well as the calculated output, which are the last three on the top here. For example, the injected quantity. The colors and the numbers indicate how strongly correlated each of those design variables is with the output. This is very useful because now at a glance, for example, you can look at the poppet diameter and determine that it is your most highly influential design variable, having impact on all of the different outputs. On the other hand, and this can be quite counterintuitive, it reveals that the poppet half angle, which was this yellow angle, has, as you see from these three blue values and very low numbers, almost zero impact on the outputs. So this is one of the ways that Optimus is going to help you to streamline your work. It'll help you to focus in on which variables are most important and potentially allow you to simplify your design because you don't have to solve for a non-influencing variable. The other way that the DOE can be used is in the creation of a response surface. Response surface is a mathematical model. It's an interpolation of the discrete data that you obtain from your DOE into a continuous multi-dimensional surface. So now you can look at any parametric combination and get the calculated or theoretical output based on this response surface. This response surface, by the way, goes by a number of different names, sometimes called a meta model, approximation model. This is extremely powerful because now, after running your DOE, you can get parametric data in less than a second, and in fact can be run on a cell phone processor. Anybody in the organization can now do parametric studies based on that model. So the response surface model, which Taylor will talk more about, is extremely powerful. It allows you to greatly speed up your analysis. In addition, you can do the optimization that Optimus was originally designed for on this surface, allowing you to get the best potential results. For example, you might be looking at this red zone, and very quickly, and then you can validate that with experimental or further direct simulation based on the physics. So this is a very powerful capability that Taylor will talk a bit more about. On the optimization side, what the software actually does for you is essentially what you would do manually, and that is to look at different designs, make decisions based on what you see, and change your parameters and run that again. And that's what Optimus does. In this example here, some work we did with Navistar, we looked at flow over a truck. This is a CFD example, wanting to minimize the drag coefficient but maximize the size of the sleeper cab, which is in the rear section over here. So on this chart here, we're looking at drag coefficient, and on the x-axis is each subsequent run of the software, the CFD software. And this merely shows you how Optimus has taken control and is now looking at the different geometries and making decisions about how to change that with the goal of minimizing the drag while optimizing the volume of the cab. So you can imagine leaving work at 5 o'clock, telling Optimus that, yeah, I want to minimize the drag and optimize, maximize the sleeper cab, come back the next day and have your best designs ready to go to the next step. Another graphic that is useful is this one right here. This shows you the progression that is typically taken. When you do your first simulation, you have a baseline case. And here again, we're looking at that same example of drag. In this case, drag versus volume, which are your two objectives. The software then conducts the design of experiments, and from that, obviously, you're going to get a better result, which is here in the middle. And then you can go to rigorous deterministic optimization, where the software then sequentially continues to look for the best designs. Now, in a case where you have two objectives, you don't actually end up with a single best design, but rather a trade-off curve. And that's what's created at the end. It's technically referred to as the Pareto front. All of the results that fall on this front, the most outward envelope, are optimized results. But they're part of that trade-off. So depending on what your engineering requirements are, whether you favor the lower drag or the higher volume, you can pick based on your requirements. So that's the end result of running optimization, is this Pareto front, and that's what you're left with to work with very efficiently. Most engineering problems are actually not deterministic, but stochastic. There's some probability, there's some range of inlet conditions, for example, and these types of problems can also be handled by Optimus. In this case, Optimus will find the best design, but then look at the range of outputs, and if some of these fall into what you have predefined as a failure domain, such as a cost function or a stress point, the software will continue to search until it finds another best design but one which ensures that your reliability is met. So very useful for your Sigma studies. Finally, I mentioned that there was some customization capability. This is very important for many companies that have many, many engineers. They want to use a common interface that everyone is familiar with, and probably the most widely used is Excel. So we do have a full Python library that allows you to create a very simplistic input and output format based on, for example, Excel. Here you would go in and merely expose those design variables of interest. The user then changes those in Excel, hits the run button, and the results are brought back into Excel. So the user never has to use Optimus and never actually has to use the individual pieces of software. So a great deal of obvious savings in time, but more importantly, getting people that are not that expert or part-time users able to take benefit of it. So that's my very brief introduction. I hope that I've given you some insights into how you can reduce the overall time through process integration, automating the entire process, through your design of experiments and the creation of response surface models, allowing Optimus to find the optimal designs and take into account stochastic aspects, customization, such as you saw with the Excel example. And all of this, of course, also reduces the amount of time that the engineer has to put into just running programs and babysitting them, and ultimately can give you much higher performing designs. So at this point, I'm going to pass the ball over to David, who's now going to give you an introduction into JMAG and PowerSys. So David, over to you.
Thank you for that introduction, Mike. So I'm hoping that everyone now, you should be able to see my screen as an introduction to JMAG and Optimus, and hear me on your phone as well. So anyway, as Mike mentioned, my name is Dave Farney, and I'm going to be presenting an introduction to JMAG working with Optimus. In my presentation today, I want to go into a little bit of a background on who are we. I mean, who are the makers of JMAG? I work for PowerSys. I work for JSOL. Who are these actors in this scheme? But I'm going to talk a little bit more about the JMAG electromagnetic analysis platform, as well as providing an example of how to generate a model in JMAG Express. I'm then going to introduce our two optimization cases that Taylor is going to get into a little bit more detail on as far as the actual optimization in Optimus. These two cases are a surface permanent magnet machine, which I'll abbreviate from here on out as an SPM machine, and a solenoid actuator. But again, first off, who are we? Well, JMAG is made by the JSOL Corporation. The JSOL Corporation was established in July 2006 as a split from the Japanese Research Institute, which was established in 1969. JMAG itself has actually been around since 1983, so we recently had our 30th anniversary, so it's actually been a package that's been in existence for quite a while. It is actually the #1 electromagnetic analysis package in Japan, but it's making its inroads to the rest of the world slowly over the last few years. In any case, the JSOL Corporation has offices in Tokyo, Osaka, Nagano, and Sapporo, and its main business units are IT consulting, system integration, and computer-aided engineering, CAE, or basically what the JMAG falls into. JSOL handles the distribution of JMAG within Japan, but outside of Japan, they rely on a network of distributors. The distributor for both North America and Europe is PowerSys Solutions. The main office, of course, for PowerSys then is located in Southfield, Michigan. The main office for PowerSys globally is located in the south of France. PowerSys has been the distributor of JMAG since 2006 in Europe and since 2009 in North America. As you would expect from the distributor, PowerSys' main mission is business development, sales management, pre- and post-sales support, JMAG promotion at various events, technical support and training services, as well as partnering with JSOL to ensure that our customers' needs are being met. For more information on JMAG, you can visit the JMAG website at www.jmaginternational.com. On the website, you'll find information on product features, an application note catalog with more than 160 examples at this point, trial license request information, as well as information on upcoming conferences and events. Now, let's talk a little bit more about the JMAG electromagnetic platform. JMAG can run electromagnetic analyses in multiple applications, including motors and generators, actuators, transformers, induction heating, sensors, EM shields, and any other type of electromagnetic analysis. The functionality built into JMAG are magnetic, electric, structural, thermal, and multiphysics. By multiphysics, I don't just mean that we have the ability to perform multiphysics analyses within JMAG, but I also mean that we can link to other programs. This is a small cross-section of the type of analyses that we can run within JMAG. As you can see, we can do everything from at the top here, linear electric machines, rotating electric machinery, speakers, transformers, voice head coils, even bus bars. So effectively, again, any type of electromagnetic finite element analysis, that's our bread and butter. So if we take a look at the JMAG product line, if we start at the base, we'll have JMAG Express. JMAG Express is a template-based analysis tool wherein you have a selection of common rotating electric machine templates that all you have to do is select the dimensions. So numerically changing the dimensions, applying the materials from the material database, applying the winding conditions, and then running the analysis. The analysis within JMAG Express is what we would consider a very quick or rudimentary analysis of rotating machine performance. Once you are able to identify a range of machines that meet your performance criteria, you can then move into JMAG Designer for a more advanced finite element analysis. So again, we can take our models from JMAG Express, move them into JMAG Designer, and then run the analysis or a more comprehensive finite element analysis in JMAG Designer. We can also pull geometries from the inbuilt 2D and 3D geometry editor in JMAG Designer, or from a separate CAD link. And these CAD links could include anything from a direct link to ProE, SolidWorks, CATIA, NX, etc., or bringing in neutral file formats like .sat or DXF. Once we run the analysis in JMAG Designer, we have this very nice finite element analysis. We want to link it to other programs. Well, one way we can do that is to use our JMAG RT motor model block. What the JMAG RT motor model block is going to do is take the operating performance of our machine and create effectively a lookup table. This lookup table will be brought into a block form that then can be brought into our JMAG RT viewer, where within RT viewer we can create simple torque speed curves, efficiency maps, or basically plot performance across the operating range of our rotating machine, or it can be taken into other programs for software-in-the-loop simulations, circuit simulators such as MATLAB's Simulink, PSIM, or National Instruments' LabVIEW, or we can bring it into hardware-in-the-loop simulations where now we're taking a physical electronic control unit or controller and pairing it with a virtual machine representation. So beyond that, again, we also have the embedded link within CATIA v5, so this again ties into that CAD link that I had mentioned a little bit earlier. But on the simulation side, we can also link with other programs such as LMS's Virtual Lab for noise and vibration modeling, Abacus for structural and thermal analysis, and of course Optimus for optimization analyses. So I think as Mike alluded to, they're a separately owned company, so they're very agnostic when it comes to working with anyone else, and that's where JMAG positions itself as well. So JMAG's focus is on electromagnetic analysis, but we recognize that the overall system design is very critical to our customers, and thus we feel it necessary to partner with leading companies such as Optimus to ensure that our customers are able to perform the analyses that they require. So let's start with a JMAG Express model and see what it's like to create a model in JMAG. In JMAG Express, as I mentioned, is a template-based analysis program. So we choose the motor type based on a library of common machine topologies. These machine topologies include brushless motor IPM, or interior permanent magnet, brushless motor SPM, or surface permanent magnet, brushless motor outer rotor, induction machines, switch reluctance motors, brush motors, and universal motors. Once we choose the topology, we can then choose the actual specific stator and rotor configuration. So depending on the magnet shape and orientation, we can change that in a PM machine. We can change the stator, lamination shape, etc. So once we pick the actual physical geometry, we can then move to set the geometry based on the numerical tables. We can use the materials from the JMAG database and automatically apply the materials. We can set the winding condition and the drive settings. So once we've actually gone through and set up our machine, we then have the ability to click on the little light bulb button and run a very short lumped parameter analysis. So effectively, we're able to set up the model in just minutes and capture the result in a matter of seconds. Before I get into the results, I also want to mention that for people that are a little bit concerned that they don't have the actual physical geometry or machine conditions, there is a sizing tool in JMAG Express where you can input parameters such as the overall output power, rotational speed, and outside diameter, and JMAG Express will estimate a machine that meets those performance criteria. Now, once we get the machine set up, again, we can look at the results, and we can see that we get a lot of very useful results when we're doing that initial machine design. So things like torque versus current, efficiency versus current, copper and iron losses, phase-rated voltage, MMF, inductance, torque constant, voltage constant, etc. So all the basic parameters that you would need to get an idea of the machine's performance. But again, this is a lumped parameter analysis, so what we're trying to do is we're sacrificing accuracy in the name of having a very fast analysis. Once we get to the point where we feel that the parameters roughly meet our expectations for the machine, we can move into JMAG Designer for a more comprehensive analysis. To move into JMAG Designer from JMAG Express, all we do is we move a little bit to the right. So instead of using a light bulb to calculate the model, we click on the JMAG icon to move the model into JMAG Designer. Once the analysis is in JMAG Designer from JMAG Express, all the settings are set. So everything has been set based on the model in JMAG Express, so all that's left to do is actually run the analysis. Once we're in JMAG Designer, there's several advantages that we like to talk about. We usually group these into 4 broad categories, which are precise analysis, an open interface, high-speed processing, and high productivity. Given that this is more a demonstration of Optimus and optimization, though, I won't get into any of these specific advantages, but I just wanted to mention them. If we go now we can shift gears and look at the 2 models that we're going to look at for the optimization study. So the first model I want to talk about is a 3D surface permanent magnet, or SPM machine. So we've created this model in JMAG Express, so we basically set up our initial 2D model in JMAG Express. Once we bring the model into JMAG Designer, we can extrude the model from a 2D model into a 3D model. Again, this can be accomplished with the inbuilt geometry editor within JMAG Designer. We can then run a full finite element analysis and simulate things like electromagnetic torque based on a 30 amp peak sinusoidal excitation. The captured output torque waveform from this motor is the following. If we look at this torque waveform, though, we can see we have a little bit of a peak-to-peak torque. It's not necessarily bad, but it might be something we want to reduce. If we wanted to reduce the torque ripple, there are several typical ways that we can do this. In this optimization example, we'll add a stator skew of up to 20 degrees to try to minimize the peak torque. At the same time, we'll also take a look at trying to minimize the iron loss as well as trying to minimize the peak-to-peak torque. The flow for the JMAG model flow for optimization is as follows. Our first step is to build the model either in JMAG Express, the internal geometry editor, or a separate CAD package, bring the model into JMAG Designer for the full finite element analysis, and then once we're in JMAG Designer, we can set the conditions for the optimization, which include the input parameters and output metrics. Again, when we're choosing the input parameters and the output metrics, if some of the input parameters are related to the geometry, we can actually use that link to the geometry editor in order to modify the geometry. So again, we're able to optimize geometric properties on these models. We can also link back to that CAD model if we have a separate CAD link. So again, if we have a direct link to a program such as SolidWorks, we're still able to optimize geometry by linking back to the original SolidWorks model. Once the conditions for the optimization have been set, we can export the model file, and then Optimus would use this same JMAG model file for the optimization analysis. So for the surface permanent magnet machine, just as a short summary on that, the input parameters are going to be the stator skew angle, and the output parameters are the average iron loss and the peak-to-peak torque. In the second example I want to talk about today, I wanted to go a little bit beyond the rotating electric machines for people that aren't just working with machines, and talk a little bit about a different type of electromagnetic model, this being a solenoid actuator. So again, for this optimization study, we're going to try to reduce the analysis time. So instead of using our 3D solenoid, we're going to use an axisymmetric or a 2D axisymmetric model of the solenoid. You can see the solenoid, we have our core, our coil, our yoke, and our moving plunger. And in the 2D model, we're going to rotate this axisymmetrically about a center line. The optimization metrics that we're going to look at for this analysis are, we're going to try to maximize the closing force, which is our force in the y direction, our force that is in the direction of motion for the plunger. We're going to try to minimize an unnecessary force. So our X force isn't really useful to the overall performance of the machine. It's just kind of an extraneous force that we'd have to deal with in the mechanical connections. And we're also going to try to minimize the plunger volume. So effectively, we want to generate the most efficient plunger design possible to maximize the closing force and minimize that unnecessary force. In order to do this, we can change the geometry of the plunger and the material properties to try to minimize the volume of the plunger while obtaining the maximum closing force. To change the volume of the plunger, we have a H, which is effectively the height of the plunger, our width 1, which is the width of the first tooth of the plunger, and our W2, which is the width of the second tooth. We also have a potential material list that we can export in that JMAG file, then that Optimus would have the ability to choose from that material list. So as a summary, in our solenoid actuator, we have our input parameters of height, width 1, width 2, and the materials, and their output parameters of the force Y, force X, and the plunger volume. So at this point, this concludes the introduction to JMAG and the initial models that we'd be using for the optimization. So I'll turn it over to Taylor, who will get into more detail on the actual physical optimizations.
Excellent. Thank you, David, and thank you, Mike, as well for the introduction. We're going to really build on what David has talked about here with those two models, and actually build on what Mike has talked about as well. And what I'd like to do is show that there are a number of key features when you combine Optimus with JMAG. These really are two best-in-class tools. And Optimus provides a platform that's extremely easy to set up when it's combined with JMAG. You'll have and you'll see how we can very quickly change dimensions, change materials, link in with other tools, link in with JMAG, and really capture what would otherwise be a complex process. When you combine these two software packages, you have the ability to run extremely fast simulations. David didn't spend a whole lot of time talking about some of the advantages of JMAG in terms of speed, in terms of the amount of time that it takes to calculate those models, but Optimus builds on that and allows the user to, in some cases, as you'll see, calculate thousands of designs in a second, or in just a few moments. Optimus is also extremely flexible, and as David talked about JMAG being able to incorporate with other tools, Optimus has that same capability. In addition, it has some data mining capabilities, so you can bring in data after the fact, and you can also combine Optimus with in-house tools and processes, and even link them in with JMAG. So David's already begun to talk about the two models that we have, this 2D actuator and this 3D SPM, and we'll get into those models in a moment. But I just want to give you a little bit of background on the process that we're going to be going through today. In order to give you that background, we should probably familiarize ourselves with a few terms. Optimization, of course, is the iterating design parameters in order to get a better performing design. That performance can be a single response or multiple responses. An analysis of a model that's solved inside of JMAG. And a surrogate, this is where we maybe get into some new terms here. A surrogate would be an alternative to a physics model. A response surface model is a type of surrogate model. So it's a mathematical model that simulates that physics data, and I'll refer to that as an RSM. And then a design of experiments is a statistical population of a parametric design space, or of the parametric design space. And we'll spend a little bit more time explaining those in a moment. Now, I would also like to mention the need for automation. We all have about 8,700 hours in a year, and typically we'll be working for about 2,000 of those hours. with a few hundred hours reserved for meetings and communications and things like that, we're actually typically only getting about 1,500 hours worth of work done in a year. And that leaves an enormous amount of time where if we could automate some of our highly repetitive tasks, we could allow that to run and increase our productivity significantly. And so we'll talk a little bit about automation, and that's actually a key to this optimization process that we talk about. The first step, of course, is to capture the workflow. Then after that workflow is captured and you can automatically run many different designs, you can then move on to conducting a design of experiments. After you have that statistical coverage of your design space, we can generate you can generate a response surface model, which will allow you to perform an optimization that could include many hundreds or many thousands of calls that can be done on a response surface model in just a few moments. Then, of course, is testing the reliability of the response that you get. So whether that's validation or whether that's some sort of robustness analysis, that's the final step in our optimization process. So the first thing that we'll talk about here is this volume optimization and reliability assessment of this 2D actuator that David's introduced us to. He pointed out the height and the two widths of this plunger and briefly mentioned the material. We won't spend a whole lot of time on the material here, but I do just want to point out that Optimus, in addition to being able to parameterize or being able to change the numeric values for H, W1, and W2, Optimus also has the ability to vary the material that's involved as well. And of course, the objectives, we want to maximize the plunger force, the Fy force, and minimize the force in the X direction. And then ultimately, we want to minimize that overall plunger volume. So the first step of our optimization process is to capture the workflow. And this actually brings us to the user interface of Optimus, which you should be able to see on your screen now. This gives us the primary screen here is the graph area, and that's where we will actually recreate or grab our workflow. And so we'll begin with the control side. So this is where we define our inputs and connect that to a JMAG project file. So Optimus will actually, when this icon is placed on the workflow, Optimus will actually interrogate the project file and identify any parameters that have been identified or that have been selected as input parameters. After that's done, of course, the call to JMAG itself, so the actual analysis. So here, Optimus writes out a new project file, runs the JMAG analysis, and then when it's finished, examines the resultant JMAG project file. And from inside of that file, it can identify, again, any of those parameters that have been selected to be exposed. So in our case, we've exposed the force in the Y direction, the X direction. We're calculating the plunger volume, and then, of course, we have that loss coil calculation as well. And then, kind of as an added feature here, Optimus has the ability to communicate any of this information at any point throughout the process back to the user. So whether that's sending an email or sending a text message, or perhaps even initiating some additional workflow, Optimus has the ability to do that. So for our baseline case, you can see the numbers that we have here for the X force, the Y force, and the volume. That's where we're starting from, and so that's what we want to potentially minimize, maximize, and then minimize the volume as well. So the next step in our optimization process is the design of experiments. To give you a little more background, building on what Mike talked about earlier, A design of experiments is a statistical coverage of your parametric design space. So ultimately what that means is that we run different experiments inside of that design space. And the points can be selected in a variety of ways. Most people are familiar with the factorial design of experiments, essentially where a point is placed in each of the corners of the design space. A 3-level factorial, for instance, simply places 3 points along each axis throughout the design space. Perhaps in the bottom right you can see a random design of experiments. This is where points are randomly selected throughout that design space. For the actuator, what we've selected is actually a Latin hypercube design of experiments. This Latin hypercube intelligently, in kind of a half-random, half-statistically significant way, places points throughout the design space. We did 100 different experiments throughout our design, and it took about 10 minutes to complete. And what we found is that there was a very high correlation between the force in the x direction and the force in the y direction. What this means is that we will have a competing objectives. So this really is a great case for a multi-objective optimization. And in the image there, the images there on the right, you can see some of the different designs that were tested. So you can see how this design of experiments navigated through the design space. After we have our design of experiments, we can move into creating a response surface model. Now, the response surface model is probably the best way to describe it is to refer back to Excel. Hopefully everybody has used or at some point seen the add trendline feature inside of Excel. What the add trendline feature does is it approximates a function through a given set of experiments or a given set of design points. The response surface model does the exact same thing, only in multi-dimensional space. And where the add trendline can only do one type of mathematical approximation, Optimus gives the user, in multi-dimensional space, of course, many different mathematical tools to approximate the design space. Approximate the response surface. In fact, Optimus has a wizard inside of it which actually automatically tests 11 different types of response surface models and attempts to minimize the error that's found in those models. And so what we found for this design of experiments was that a random forest response surface model was used for fx and fy, which you can see in the upper right, and our neural network was used for the volume calculation, which is the image in the lower left. And so now that we have this surface, this actually becomes a mathematical function that we can very quickly calculate on. So the next step is to move into the optimization. We conducted a global optimization using one of the many optimization methods inside of Optimus. And there were actually, it was a challenging optimization because there were 3 different objective functions. And so we end up with kind of this helical Pareto front, which you can see on your screen here. All of the points on this surface are actually the optimal point when it comes to volume, force in the x compared with force in the y. What's interesting here is that we were able to run 5,000 iterations in about 2 seconds. Because it was running on that response surface model, all of these points were estimated instantly. And here you can see a 2-dimensional version of that same chart. The baseline image is highlighted in gold, and then the optimal image is highlighted in blue. And you can see how Optimus navigated this optimization space and found points. It actually found multiple points, and we selected one of them that was the optimal or the best point. And the numbers, we were able to slightly reduce force in the x direction, slightly increase force in the y direction, and significantly reduce the volume of that plunger. In the image on the bottom, you can see the original or the baseline plunger compared to the optimized plunger. And so the final step in our process is to determine the reliability. So the example reliability scenario that we have here is that we want to make sure that none of our, or less than 10% of our plungers are larger than 17.9 units. And so we take we assume that we know the manufacturing tolerances that were used to create this plunger, and we apply that distribution. In this case, it's a standard normal distribution with a standard deviation of 0.01. We apply that distribution to each one of the input variables, and then we run 5,000 different experiments taking into account the distribution here. And what we found is that when we apply this distribution, only about 6% of the designs were larger than that 17.9 units. And so what this tells us actually is that our failure, or probability of failure, is only about 6%. So that's within the range, which we had previously determined to be 10%. So to give you an overview of the amount of time that it took, hopefully you could tell the ease for each one of these processes. There really were a minimal number of button clicks to get there. But it took about 10 minutes to capture the workflow, only about a minute to set up the design of experiments, of course, and then it took about 10 minutes to run, 5 minutes to create that response surface model, 2 seconds, as we mentioned, to run the optimization, and then finally about another 10 minutes to perform the reliability assessment. So we were able to do the entire process really in less than 30 minutes. So the impact of using Optimus with JMAG, we were able to reduce the volume by 46%. We were able to automate or capture the entire process, which took less than 30 minutes. And ultimately, we were able to determine a 6% failure ratio for the design, the optimal design. Now, for the SPM, we wanted to highlight a few additional features of Optimus. And to show how you can gain design knowledge from simulation results that you already have, in addition to capturing the process. So Optimus, you have the ability to import data from external sources. All of the past data that you've had for the many years that you've been using JMAG, that data is not lost. In fact, we're able to synthesize knowledge from all of the existing models that you have. You can do this by creating, as we've seen, creating the response surface models on that past data. And you can even run or conduct optimizations on that model. And so David was talking about how we wanted to vary the skew angle on this SPM by about 2 degrees. What we found was that the initial model took about 3 hours to solve for each increment. Now this, of course, comes because there was about 1.3 million elements. So this was quite a refined JMAG model. And so we actually ran this model at 2 different locations. And when we were complete, when each location had finished solving, we combined the data into a single table, as you can see here. And that data, of course, was then imported into Optimus to really highlight that you can bring in any data set. After that data set has been imported into Optimus, you can create this response surface model that we've been talking about. In addition, you could export that response surface model later on so that others could use it as a function. And you also have the ability to estimate what the response would be for any given skew angle in the entire design space. So even though we only tested 0 degrees, 2 degrees, 4 degrees, etc., you can actually calculate what the response would be for any skew angle. The two response surfaces that you see here were created using a mathematical function called a radial basis function. And you can see they're somewhat opposed, the torque ripple on the left and the core loss on the right. When we ran the optimization on this response surface, this is the Pareto front that we developed. We used an optimization method called particle swarm optimization, as we were attempting to minimize the torque ripple and minimize the core loss. You can tell, based on the color of the bubbles, the progress of the optimizer. So basically, the darker red bubbles indicate that we were further along in the optimization process. And so because this is a trade-off, so each of those points represents the lowest torque ripple for the lowest core loss, we selected 3 different points for a trade-off. And you can see those points there. That's point 227, 205, and 218. And you get an approximate idea of where they're located on that Pareto front. And so we wanted to test and see just how good this response surface model was. And so we selected one of the points, 205, to validate. And what we found is that when we took the estimated response from the response surface model and ran that inside of JMAG, we found that the response surface model was off by less than 1%. So it was an extremely accurate response surface model. So in conclusion to this case study, we showed that you were able to import any past data into Optimus, create an RSM, and then on that data, and solve the models extremely fast. And hopefully with these 2 case studies, you've been able to see that when you combine Optimus and JMAG, first, they're extremely easy to combine. You can set them up very fast and create repeatable workflows. Second, these 2 software packages combined are extremely fast. They allow you to calculate thousands of designs in a very short amount of time and really conduct an unattended parametric analysis and optimization. And ultimately, that the 2 software packages are extremely flexible. We've shown that you were able to import external data, that we were able to do some reliability and robustness assessments. Mike talked a little bit about some of the additional integration that we have with things like we have a full Python API and Excel. So I'd like to thank you for your time. This concludes my portion of it. I'll actually turn the turn the mic back over to Mike, and maybe we can field some questions and answers.
Okay, thanks, Taylor. We do have 10 minutes left, or a little less than 10 minutes, and thank you for those that have sent in questions. Let me encourage you to continue to send in questions. Even if we don't get a chance to address them now, we'll certainly follow up with an email or a call. Okay, well, let me try to quickly scan these questions to hit the most general ones first. Okay, here's a question regarding trials. Are trials available? In fact, while it is often very clear to see the potential benefit that Optimus brings, it is often a bit trickier trying to quantify the real impact it would have. And as such, we are actually very much in favor of doing some kind of trial or pilot study, obviously under the right situation. And I would encourage you to contact us directly if you'd like to discuss having a trial. David, on your side, I know you had mentioned that, but if you'd like to say a few words about trials.
Yes, I agree. It's trial licenses for us are very useful. We also actually try to work a lot with benchmark studies. So we can build your model and then create the results, and that prevents customers from having to go out and try to learn JMAG at the same time trying to reproduce results from one of their existing machines. So we're very active with supporting trial licenses and providing benchmark studies that can act as a kind of a segue to get started within that trial license.
Okay. Here's one over to you, Taylor. In what ways can parallel processing be utilized by Optimus?
That's a great question. We didn't spend a whole lot of time today talking about it. Optimus has the has the ability to incorporate parallel processing in one of two ways. First, it can call the analysis tool like JMAG to be run on multiple processors. That's not a problem at all. And then second, it can also submit multiple jobs simultaneously. So for instance, if you had 4 JMAG licenses, you could actually run, Optimus could run 4 different experiments at one time. In addition to all of that, we have the ability to interact with any scheduling tools that may be available on your high performance or your high performance computing clusters. So all of that is built in, is integrated into Optimus.
Yeah, and let me just add to that and stress one point. I talked a lot about DOE, design of experiments, and response surface modeling, and indeed, one of the other advantages of DOE that I forgot to raise is the very fact that you can run all of those cases in parallel, assuming you have the proper CPU and licensing, of course. So if you had, as I had given as an example, 40 different cases, then that DOE could be run in one go with 40 different cases being run simultaneously. So it's another reason why DOE and RSMs can be utilized so heavily by Optimus and taken advantage of. Okay, let me move to the next question here. This one is over to David. I've got somebody curious about the learning curve for JMAG and how long does it take before I will have confidence in my results.
For basic parameters such as torque, back EMF, etc., typically what we find is that customers, after about 2 weeks of working with JMAG, are able to get the basic parameters. So JMAG is really tailored to be a tool that can be very quickly picked up based on being intuitive and easy to use, but also have enough power that even advanced users can always find more to simulate and more accurate ways to simulate things. But typically what we find is usually companies come back and say after about 2 weeks of working with the software, they're fairly confident in the results that they're getting and they usually get pretty good correlation with the measurement data that they're using.
Okay. This one is back over to you, Taylor. You spend a lot of time talking about response surface modeling, but how do I ensure that I have a quality RSM?
Optimus has a number of built-in measurement tools. The typical, when it comes to modeling or approximating a surface, typically you have a value called the R-squared value. Optimus reports that data for all of the response surfaces. In addition, we've gone above and beyond with some of our RSMs where we calculate what's known as a leave one out, or the leave one out error. Basically, we'll take the response surface and just remove one of the known points, calculate the difference between what the surface would calculate that value to be and what that value actually was. We'll go through and do that same process on every single point, summate that data and return that, and that's known, of course, as the leave one out error. So there are a number of different ways that we can determine that quality, and all of that information is fed back to the user.
Right. I think it's an excellent question because we do stress, indeed, the use of response surface modeling. And I guess the quick summary is we provide, or Optimus provides, very effective feedback so you know whether or not you need to further modify that, add additional points, or just be skeptical about the results or have confidence. So it is an area that we've invested a lot of our development because RSM is such an important aspect of getting the speed ups in time. I think we have time for just one more question. Let me go ahead, and I've got a couple others, but as I mentioned, we'll respond back via email or by call. But one over to you, David. Are there limitations on what can be optimized in a model?
Not really. So I think we've seen a pretty good example of pulling in a geometry optimization, a material optimization, and a parameter optimization. So we find that the limitation on the optimization is just what it can be set up when it comes down to it. So otherwise, I think setting up the appropriate boundaries to make sure that if you're doing a geometry optimization that you're not going to come up with unsustainable geometries. That's really the limitation, is just whatever can be created. So.
Okay. Now, a couple of you have asked about pricing, and obviously that's always an important question. The reason I really don't like to directly give you an answer on that is that it varies so much. One of the beauties of Optimus is that it's very modular, and you only pay for those aspects of the software that you need. And therefore, the prices can range quite a bit. So I would encourage you to simply contact us directly, and we can look at what type of capability you need and what the resulting price would be. And David, just real quick, if you could also respond to that question regarding pricing.
We're kind of in a similar boat. So JMAG is a modular software package, which means that whatever the analysis that you want to work with, whether it be magnetic, electric, structural, thermal, etc., those are the modules that you can purchase. And so typically we like to say that it's always difficult because the pricing isn't linear, and we do have various options, including leasing. But for a perpetual license, we usually like to say, as a ballpark, for 2D is right around $30,000. For 2D and 3D is right around $50,000.
Okay, well, that was very helpful. That concludes our time here. Thank you very much for attending, and I hope that you have been able to see how this would potentially benefit you. Let me just say that this presentation, of course, is very general, and it's also very one-way with us doing all the talking. We would be very delighted to have a one-on-one WebEx with you that will address your specific situation and give you a much better idea of how Optimus would help you in your specific arrangement. So please contact us, and we'll be happy to arrange that. We do have other webinars coming up. I believe the next two will focus actually on CFD, which of course is widely used in all industries. And more information, of course, is available at our respective websites. So thank you very much, and please let us have any further questions or if you're interested in a WebEx. Thanks for your attention. Bye-bye.